Hello, I'm Hikaru Ikeda of Osaka University in Japan. Today, I'd like to talk about automatic design support mechanism that can more easily design layouts using reinforcement learning. First of all, I want to talk about the background of this study. In this study, we research a solution to facility layout problems. The facility layout problem is an optimization problem of deploying equipment and machines in the facility. When you design a facility layout, the accuracy and perfection significantly depend on the designer's ability. And quick and near optimal design are difficult to create. And as a solution to facility layout problem, we aim to develop a system that can derive a layout in which rectangular units with arbitrary facility function as shown on left side of the figure can be accommodated within the site on the right side. In the next slide, I explain the reinforcement learning. Reinforcement learning is one of the machine learning methods to achieve optimal system control through trial and error by system itself. We can make the learning agent learning behavior to maximize the score in the learning environment. This figure shows an example of state transition in learning. In the learning environment, agent determines the to uh, action to taken in the current state according to the action selection policy pi. Agents obtain rewards according to the action they take and learn based on returns, which is calculated from the rewards. The most important feature of reinforcement learning as machine learning is that agents generate their own learning data. Here I will explain the learning methods. The most important point here is state representation. We represent the state as a combination of the remaining area of site and the maximum rectangle in undeployed site. In the figure, the blue area represents the, uh, the area where units have already been deployed, and the white area represents the area where units have not been deployed. The largest rectangle in the undeployed area is shown in yellow. If only the remaining area of the site is considered as a condition, there are several possible situations as shown in the figure. It is difficult to satisfy each remaining area with a uniform deployment policy. On the other hand, if the detailed site conditions are made into states, the number of states will become too large. Therefore, by introducing this maximum rectangle, the agent will have more detailed information about the site and will be able to deploy units according to the situation. And in the next slide, I'm here to talk about action value function. Action value function is a function that represents the value of action in the current state. Agent updates the action value function and optimize their action choices. In my study, action value function represents as the right figure. Row of table is state, which is represented by the remaining area size and the maximum rectangular in the remaining area. Column of the table is action, which is represented by units to be deployed. The agent calculates the average returns for each trial and updates the evaluation of each action. For example, in this figure, this value means the action value when the remaining area is 20, maximum rectangle is 1 times 2, and the agent deploy 1 times 2 units. In the next slide, I will talk about how to calculate return. Return represents some of rewards that can be earned in the future. You can calculate return by the obtained reward in the current state and the return in the future state. And this equation represents the return in the equation represents how to calculate the return. Return k represents the return in the state sk, and rk represents the reward in the state sk. And discount factor alpha is used to explain the influence on the return, and it's set from 0 to 1. The closer to the value is to 0, the less is the influence on the past states. Return k is calculated by the sum of rk plus 1 and the product of alpha and return k plus 1. Then return k plus 1 is calculated by the sum of rk plus 1, 2 and the product of alpha and return k plus 2. In this way, agents can calculate the return by the levers and the return in the next state. In our study, we set the number of deployed area as the levers Rm in the final state Sm. In the next slide, I will talk about selection policy. Selection policy is the guideline for choosing actions. We introduce epsilon grading method as a unit selection policy. In the epsilon grading method, the agent selects units based on the random number m with epsilon as a threshold. When m is greater than or equal to epsilon, the agent selects the units at random. This is called extrapolation. When m is less than epsilon, the agent selects the unit with the highest action value. This is called exploitation. I'm here to talk about starting point. Unlike Go or Shogi, it is difficult to determine the placement of units on the site because they are various sizes of units. To solve this problem, we introduce starting points. The agent sets a starting point according to the current condition of this site, and the units are deployed based on the starting point. The agent searches the site and defines the next starting point as a point that forms the largest rectangle with no units located. This figure shows an example of starting point changes. The blue area is already deployed, and the white area is empty, and the gray area is outside of the site. Then the point 02 is chosen as the next starting point because its yellow rectangle is the largest in the figure. Having said this, I will explain the mechanism of learning program. This figure shows the flow of the one trial in the episodes. As an agent places units on the site in sequence, it learns deployment priorities that will enable it to successfully fill the site. First, the agent generates a group of units. Second, the agent selects units with epsilon grading method. Third, the agent deploys the unit based on the present starting point. Fourth, the agent moves the starting point. Then the agent repeats step 2, 3, and 4 for the number of units. Finally, the agent calculates return and update action value function based on placed units. Agent repeats this trial as a specified number of times and learns a better layout design policy. Here we conducted experiments using the proposed mechanism. First, we applied the mechanism to 3 sets of units to affirm where the agent can obtain a layout. The unit are the ones Lucille D. Mirror and his colleagues used for their layout. This figure is the layout derived as their experimental result. Second, we examined the efficiency of repeated learning for one set of units, we affirmed the possibility to deeper learning for the combination of existing units by executing learning multiple times for each set of units. We learn each learning for a total of 50 million trials. There is an L-shaped unit, but my method only handles rectangular units, so I split the units into several units. Here you can see the layout result derived by the agent learning with 50 million data. From left to right, third forward, second forward, first layer layout. Sites with no units are represented by zeros, and sites where units have been deployed are represented a number based on the number of times the unit has been deployed. The results show a layout that satisfies the site in the all forward. Here you can see the graph of total amount of change of action value in the learning. The horizontal axis represents the number of trial, and the vertical axis represents each action value represents the amount of change in the action value. Each action value converts to constant value as learning progresses. To verify the learning ability of the agent, we measure the number of learning trials before the fastest fulfilled layout can be generated. You can measure the degree of learning and the degree of convergence by observing the amount of changes. The number represented as x times y under the graph are the amount of trials. X means iteration count for a set of units, and Y means number of set of units. Then the graph shows from left to right 1 times 50 million, 100 times half million, 1,000 times 15,000 studies. All three graphs initially pointed around 150 to 200 and settle around 20 to 25 over 10 million trials. And this graph plots the number of times before the agent is able to derive the layout for each iteration count. The horizontal axis shows the number of iteration count for one unit set, and vertical axis shows the average number of training iterations until the layout is derived. A smaller value on the vertical axis indicates fastest time to layout. According to the graph, outlier is generated when repeated 300 times, and other part of graph tended to increase monotonically. Therefore, it is better not to repeat learning using the same set of units. From the experiments, we found that after 10 million times of learning, the amount of change in action value converges to around 20 under different conditions, and we can derive a layout. And the number of trials before the agent derives the layout increase as the iteration count increase. And therefore, learning the same set of units continuously do not have enough effect for learning speed. Then I'd like to conclude by making the following points. First, we can create agents by proposed method using reinforcement learning, and they were able to derive layouts that fulfill the specified site. Second, we examine the effect of providing the same learning data continuously, but it does not make a large difference. Finally, I will discuss the future tasks. First, we would like to expand the scope of study and layout their variation for a single forward to multiple levels. Sorry. Second, we would like to introduce a correlation between units. In actual facilities, each unit has a function and meaning, and each unit must be adjacent or should not be close. And therefore, we would like to set the relationship between the units and modify that the agent can learn that the units can be deployed close to each other. This is all my presentation. Thank you for listening.
Thank you very much for your great presentation. Now we have time for questions. So are there any questions? So maybe one question from me. Because your problem seems to be maybe not very classical multi-agent for problem for enforcement learning, but a more general optimization problem. So I was wondering, have you tried other techniques apart from reinforcement learning to compare this approach against?
You mean another technique to?
Yes, to compare.
In this study, I use only reinforcement learning and specifically uh, and Monte Carlo methods to create a layout.
So maybe that's also maybe if you want to, that's also something for future, just to compare other methods, or maybe it's good enough.
In the future task, I want to introduce relationship between units. I said so. I think it is it need to introduce another techniques to this future task, complete this to future task.
Okay, thank you very much once again.